All right, let's talk about balancing chemical equations. I know, it can feel like a real chore, but what if we reframed it? Let's think of it more like a skillful performance, a balancing act that's at the very heart of all chemistry.
I mean, come on, we've all been there, right? You're just staring at some crazy-looking equation, plugging in numbers, erasing them, trying again, feeling like you're just guessing. It is so frustrating. But why do we even have to do this in the first place?
Well, it all comes down to one of the most fundamental rules in the entire universe, the law of conservation of mass. All it really means is that in a chemical reaction, atoms don't just disappear or pop into existence. They just get rearranged. So whatever you start with, you have to end with. Our job is just to make the equation prove that basic fact.
So, let's start with the first tool pretty much all of us are handed. The classic method of just, well, eyeballing it.
This is what we call balancing by inspection. You know how it goes. You take a pretty simple reaction, like burning propane. You write it out, count up the atoms on both sides, and start adding coefficients. You might tackle the carbons first, then the hydrogens, and you always save the trickiest one, usually oxygen, for the very end. A little bit of tweaking and there you go. It's balanced. For simple stuff, this works just fine.
But what happens when the equations get a little more gnarly? Well, if you've ever felt totally lost, you are not alone. As a researcher from Sandia National Labs put it, for complex reactions, this guesswork method rapidly becomes both laborious and haphazard. In other words, it gets messy fast. There has got to be a better way.
And lucky for us, there is. So let's start building up our toolkit with a few clever shortcuts that work in specific situations.
Okay, for combustion reactions, that's burning stuff, there's this really cool trick that was shared in a Reddit community. You just follow a simple order. Take your fuel, balance the carbons first, then balance the hydrogens by just taking half the number of atoms. Now you might end up with a fraction for your oxygen, like 3.5. Don't panic. That's totally fine. If you need clean, whole numbers for your answer, you just double everything across the entire equation at the end. It's a super fast and reliable shortcut.
So the combustion trick is fantastic for that one type of reaction. But what about all the others? You've probably noticed these big, chunky groups of atoms that seem to travel as a pack from one side of the equation to the other, completely unchanged. How are we supposed to deal with those?
This is a total game changer. If you see a group of atoms, a polyatomic ion, like the sulfate group here, SO4, and it appears on both sides of the arrow without breaking apart, do not count the individual atoms. Just treat the whole thing as one unit. So instead of 1 sulfur and 4 oxygens, you just count 3 sulfate groups. It makes the accounting so much simpler.
But look, tricks and shortcuts will only get you so far. To really tackle the tougher problems, we need a truly systematic approach, one that completely removes the guesswork.
And that brings us to the algebraic method. This is where chemistry meets math head-on. You just assign a variable, A, B, C, D, to stand in for the coefficient of each molecule. Then, for each element, you create a simple little algebraic equation. So for carbon, the 6 atoms in A must equal the 1 atom in C. You do that for all the elements, you get a system of equations, and then you just assume A is 1 and solve for the rest. No more guessing, just pure, simple logic.
Now, this method is incredibly powerful. It will solve pretty much any equation you'll see in a standard chemistry class. But it does have a hidden weakness. See, the algebraic method works by assuming there is one and only one correct answer. And believe it or not, that's not always the case. Some chemical systems are more complicated. For those, we need to bring out the big guns.
So for those really tricky situations, and frankly, for any situation, it's time to introduce the ultimate power tool in the chemist's balancing toolkit.
This quote really says it all. You can represent a whole chemical equation as a mathematical grid, called a matrix. And when you do that, you can find something called its null space. Now, you don't need to be a math whiz, but basically the null space is the complete set of all possible solutions that make the equation balance perfectly. It doesn't just give you one answer, it gives you every possible answer. It's like the master key. And when I say it can handle everything, I mean everything. Just look at this monster. It has dozens of atoms of all kinds of elements. And to make things even harder, you see those little plus and minus signs? That means we don't just have to balance the atoms, we have to balance the electrical charge too. Can you even imagine trying to solve this by guessing? It would be an absolute nightmare.
But for the matrix method, this isn't a nightmare.
It's just a calculation. It cuts right through all of that complexity and produces this, the perfectly balanced solution. And just look at those numbers. We're talking coefficients in the hundreds, even over 1,000. There is no way, absolutely no way, anyone is ever getting there by guesswork.
So, how does it do it? Well, we don't need to get lost in the weeds of the math, but the basic idea is that the entire equation, all its atoms, all its charges, gets converted into a grid of numbers, a matrix. And then that grid is solved using operations that, honestly, a good calculator or a simple spreadsheet program can handle. It turns a chemistry puzzle that looks impossible into a straightforward math problem.
And this is what's so incredible about it. This method is universal. It works for every single chemical equation, no exceptions. But even better, before it even gives you an answer, it can tell you if an answer even exists. It can tell you if there's only one solution, or, and this is wild, if there are actually an infinite number of ways to balance it.
Okay, so after all of that, which method should you actually be using? The real answer is, well, it depends on the job you're doing.
Let's think of it as your personal chemist toolkit. Inspection, or eyeballing it, is perfect for simple equations where the answer just pops out at you. The tricks we talked about are your fast shortcuts for those common problem types. The algebraic method, that's your reliable, systematic workhorse for most of the challenges you'll face in school. And the matrix method, that's your professional-grade power tool. It can handle absolutely anything chemistry throws at it. Because really, the goal isn't to become an expert in just one of these. The real skill is being a smart chemist who knows how to look at a problem and know exactly which tool to pull out of the toolkit to get the job done right and get it done efficiently. And that kind of leaves us with this one last fascinating thought to chew on. If any chemical reaction, no matter how ridiculously complex, can be perfectly described and solved using the language of mathematics, what does that really tell us about the language of chemistry itself? It suggests that the universe, on its most fundamental level, is playing by a strict, logical, and kind of beautiful set of mathematical rules.